In this video, we're going to be looking at the velocity vector of a moving object. We're going to start thinking about some real-world things, finding their speeds, the constant velocity, finding the shortest distance from a point to a line, and lastly, looking at, again, the intersection of two lines based on vector equations. So to start, if we're looking at the velocity vector of a moving object, direction vectors are also often called those velocity vectors. It's talking about which direction it's going. So if a particle moves according to the vector 4, -7 every second, then we know that the velocity of it is the square root of 65, squaring each of those, taking the square root of it. That's what it's moving. That's what it's physically moving. So the velocity, therefore, of the vector is the square root of 65 meters. Sorry, we lost that along the way. So this is the square root of 65 meters per second in the direction of 4, -7. Velocity has this speed in addition to its direction. So it's telling you it's moving 4 units to the right for every 7 units it moves down. That's dealing with the velocity itself. Compared to speed, this is becoming a little bit messy, this speed is just the square root of 65 meters per second. Speed does not include direction. If you think about it, the way I can kind of attribute it, if you talk about how fast you're going, you talk about your speed. You are going 55 miles per hour. We don't usually talk about north, south, east, west. Velocity does. Velocity also has an additional direction that's involved in there, dealing specifically with the direction vector, which is the velocity vector. So, the velocity vector of a moving object. If vector AB is the velocity vector of your moving object, then it's traveling at a speed of the length of that vector. So, square root a squared plus b squared in the direction of AB. So that those bars mean the length of that specific vector. So example here. So here's my velocity vector, or my vector equation, sorry, of the path of an object. T is in seconds, so we're going to look at t be greater than or equal to 0, and our distance is going to be in meters. If I want to find my initial position, this is kind of going back a little bit to the previous video. My initial position is where t equals 0, so I'm going to plug 0 in for that t, which means this goes away. So the initial position of this is going to be 7, 5. It's the vector 7, 5 because it has that initial starting point of 7, 5. Part B, find the velocity vector of the object. The velocity vector is just this part that's attached to that multiplier, that constant. So that's going to be 6, -8. That's the velocity vector. The speed, part C, is the length of that velocity vector, which is 6 squared plus -8 quantity squared, which is 100, which is 10 meters per second. In the direction, oh, that's speed, I'm sorry. So there's no direction in this case. And then part D, if that object continues in the same direction, so the direction is staying the same, but it's increasing its speed. So this direction, initially here was 6, -8. It's going faster, it's speed. So the square root of this has to equal 30. In order for that to happen, my speed is increasing 3 times as much, so it's 3 times the velocity vector. So when I multiply that through, I get 18, -24. So that's my velocity vector of this specific object. And if you want to check it, take the square root, 18 squared plus -24 squared, you'll end up with your 30. Now we have an object initially starting at 5, 10, and it's moving with the velocity vector 3i minus j. Find the position after t minutes. So the position, xy at any point in time, is my initial 5, 10 plus t times my velocity vector, which is 3, -1. So therefore the position of the object, my x value itself, is going to be 5 plus 3t. The y value is 10 minus t. So the position at 3 minutes, plugging 3 in for my t, 5 plus 3 times 3, and then 10 minus 3 is 14.7. So that's my position 3 minutes into it. In part C then, I want to know the time when the object is due east of 0, 0. So real quick here, here's east, it's due east, which means it has to be somewhere along here. If that's the case, you know it's not shifting up or down at all, which means your y value has to be 0. So for part C here, the y has to equal 0. So 10 minus t equals 0. When does that happen? When t equals 10. So 10 minutes later is when it's going to be due east. We can also look at closest distances. If you remember, the closest distance is when PR is perpendicular to AR. So I have to figure out where does R have to be so that these two are perpendicular. I need them to be perpendicular. If they're perpendicular, we learned that before, that their dot product is going to be 0. So the dot product means that if the dot product is 0, that means those two are perpendicular lines. So here's our example. I want to look at ship R moving in the direction 3, 4. So for every 3 over, it's 4 up. Its speed is the square root of 10. Find an expression for the position of the ship in terms of t and the number of hours after leaving the port. So I'm starting at A. So I'm starting here. So I'm starting at -8, 3 plus its t times my velocity vector. Keep in mind, please, that my speed is 10. In order for my speed to be equal to 10, I have to take this vector and multiply it by some scalar so that when I take the length of this, it equals 10. In order for that to happen, I have to double it, which means my velocity vector is actually going to be 6, 8. Because again, if I check that, 6 squared plus 8 squared is 100 squared, square root of that is 10. So my velocity is correct, and it's 10. It's going in that direction of 3, 4, which is the same thing as the direction of 6, 8. It's just shrinking it down in size. So for part A, if I need to know the number of hours here based on t, then I know this is -8 plus 6t, comma, 3 plus 8t. That's the location of R. This is where my R value has to be at. Okay, so that's the value that R is going to be at, somewhere along here. If I want it to be the closest to port P, okay, maybe I need to move this dot just a little bit. I need to make sure it is perpendicular. So therefore, this is my R value, not up here. My R value is down here. It's -8 plus 6t times 3 plus 8t. That's the location of it. So if I want to figure out the time, the t value, when it's the closest, I need to find to port P, I need to find from P to R. So I need to find, for part B here now, I need to find vector PR. I need it to be the closest. So if I need to find vector PR, I need to take my R value, which is -8 plus 6t, and subtract the P value, which is 10. And then I have to take my Y value of it, which is 3 plus 8t, and subtract 2. If it's the closest, I'm doing the dot product. I'm figuring out when this vector here, is perpendicular to this vector here. That vector is my R, which is 3, 4. And I know, slide this over just a minute, that this dot product has to equal 0 for these to be perpendicular. So here's my vector PR. This is my velocity vector. I don't know if we call that something. No. That's my velocity vector, and I know the dot product has to be equal to 0. So now I'm going to simplify this just a smidge. Therefore, this gives me 6t minus 18 over 8t plus 1. Then I'm going to dot product that with 3, 4, and that has to equal 0. So 3 times 6t minus 18 plus 4 times 8t plus 1 has to equal 0. Combining all that together, I get 50t minus 50 equals 0. So t has to be 1. It's 1 hour after the ship left the port that they will be perpendicular. That'll be the shortest distance away. Okay, next, if we have a point P and the line with parametric equations, x, y, and z, so now we're looking here at three-dimensional things, find the coordinates of the point of the foot of the perpendicular from point P to the line. So here I have a point. I'm going to have to kind of draw this two-dimensionally from a three-dimensional scale. I've got this point. I want to find out when is it perpendicular. Where is the foot of it? Right here, perpendicular. So here's my point P, which is -1, 2, 3. And then I have the line that's made up of the parametrics for my x, y, and z value. So therefore here it's 1 plus 2t for x. My y is -4 plus 3t. And my z is 3 plus t. So I need to figure out when these two are perpendicular. So that makes up that coordinate point. So if they're going to be perpendicular, I have to find the vector from P to A. And to find the vector from P to A, I have to subtract, take my A value that we're trying to find here, and subtract the P value. So therefore vector PA is 1 plus 2t minus a -1, -4 plus 3t minus 2, and 3 plus t minus 3. So therefore vector PA is 2 plus 2t, -6 plus 3t, and t. Then I have vector B, which is this velocity vector, and that deals with the multipliers, which is 1 there. So this is going to be vector 2, 3, and then 1 is that coefficient. So if they're going to be perpendicular, this is my B vector, I'll call it. Vector PA dot vector B has to equal 0. So when I do my dot product, I'm going to kind of skip a couple steps here. 4 plus 4t minus 18 plus 9t plus t has to equal 0. Therefore t ends up equaling 1. Lastly, find the shortest distance from P to the line. It asks for the coordinates of that, so I had to then plug the t in to find that was the time it took. So then once I plugged the 1 in to this coordinate point, I end up getting A equaling 3, -1, 4. And then lastly, I wanted to find the shortest distance, not necessarily just the location, but where it happens at. So I need to find, therefore, vector PA. Vector PA ends up being 4, negative 3, 1, going from P to A, doing the actual subtraction. And when I find the length of it, 4 squared plus 3 squared plus 1 squared is the square root of 26. So that's the length of PA. So this is PA, not the vector PA. We looked at finding the intersection of the two equations before in the previous video as well. In this case, we can set up each of our individual parametric equations and solve for S and T. So in order to figure out the point where they intersect, figuring out what that x and y value are, they have to be equal. So negative 2, 1 plus that S times 3, 2 has to equal 15, 5 plus T times its velocity vector 4, 1. So when I go through and I look at each of the individual pieces, I can set up my system of equations. Negative 2 plus 3s equals 15 minus 4t, and then 1 plus 2s equals 5 plus t. Set up your system of equations, do elimination. I'll bring all my s's to the left and t's and constants to the right. So 3s plus 4t equals 17. 2s minus t equals 4. And then going through elimination, multiplying the bottom by 4. I have 3s plus 4t equals 17, and 8s minus 4t equals 16. Add the two together, 11s equals 33. S therefore has to equal 3. Take your s value, substitute it back in. I'll use this equation here before I did the multiplication. So 2 times 3 minus t equals 4. So negative t equals negative 2. T is 2. So now that I have my s and t values, I have to plug them back in, make sure I have the coordinate points. You will have to check both of them because they may be, they may not intersect at all. So take your s value and plug it in with your t into this top equation, and then plug it into the bottom equation. When you do this, you are going to get the point 7, 7. 7 for x, and then it happens to be 7 for y as well.